Okay, sheet metal fabrication. So far in this class for sheet metal, obviously you guys are working on the toolbox. Almost all of you are done. Almost. The metal that you're using for the toolbox, you notice the finish on the metal. Okay, it's kind of flaky looking and it's shiny. It doesn't really look like silver like we're used to. It doesn't really look like steel like we're used to, right? When you touch it, if that was regular sheet steel, by this time in the trimester, especially after yesterday and today, you're putting your sweaty palms on there, you're going to have all kinds of rust on there, right? Well, we don't have any rust on our sheet metal toolboxes. How come? They're galvanized. Okay, they've been rust-proofed with a zinc oxide coating. So we're going to talk a little bit about that. That's just one of the many kinds of sheet metal. Sheet metal doesn't have to be galvanized steel like we use. Sheet metal can come in precious metals, can come in aluminum. Okay, when it's steel, non-galvanized or galvanized. So we'll take a look at all of those forms of sheet metal. So your learning targets today, be able to understand the materials used in the process of sheet metal fabrication. So the different materials that we can use. Understand safety concerns of working with galvanized metals. Where else have you used galvanized metals besides in a sheet metal toolbox? Has anybody done anything else like outside of class? How about galvanized nails? Or galvanized screws? Maybe we're building a deck. Okay, or galvanized nails. If we're framing a house, we would use galvanized nails anywhere that we would be working with treated wood. Or if we're building a tree fort or a deer stand, we might want to use galvanized nails. Why? Conduit. Yeah, a lot of conduit's going to be galvanized as well. Because that's in areas that are usually moist, like in basements or against block walls. So those need to be rough-proofed as well. Why would we use galvanized fasteners for building a deck? They're going to last longer, right? They're not going to rust out. If we use regular screws or regular nails on our deck, they're only going to last a few years, or they're going to rust through, and then the pressure of movement of the materials from spring to summer and frost to thaw, it's going to break all of those fasteners. So galvanizing is a huge advantage, and we'll talk very specifically about that in a couple of slides. Materials in general. Sheet metal. Metal formed into thin, flat pieces. Thicknesses can vary slightly. We have really, really, really thin to maybe considered like foil, like aluminum foil, or even like gold leaf or something, if we're going to put gold leaf on the edges of pages of books. Or gold leaf lettering, maybe on like leather handbags or on wallets or belts. To all the way up to a quarter-inch thick would be considered, anything over a quarter-inch thick would be considered plate. So by definition, this stuff over here is sheet metal. The stuff you've been welding on, 11-gauge steel. It's about 1/8 of an inch thick. It's considered sheet metal, not plate. Have to be a quarter-inch thick to be considered plate. We can use a lot of different kinds of metals. Obviously, we use steel not only for welding and cutting over here, but also for our toolboxes. Aluminum, brass, copper, tin, nickel, even titanium. Decorative metals, precious metals, gold and platinum and silver. Any of those materials can be formed into a sheet. Some are galvanized. Our toolbox is galvanized. In order to galvanize our steel, a ferrous metal, it's dipped into a molten pool of zinc. So the zinc is molten, liquid zinc. We dip steel into that. There's a metallurgic reaction that happens, and the iron in the steel reacts to the molten zinc. And what you see is not only that finish that kind of looks kind of flaky, and the finish can vary from matte to shiny to flaky to not flaky. But what you're looking at there is a tightly bonded alloy. So now we have this alloy now, this zinc oxide, the zinc that is bonded with the with the ferrous metal. So we have superior corrosion protection. Zinc is non-ferrous, so it's not going to rust. It will oxidize, but it's not going to rust. Shane. Usually, yeah. Is galvanized better than painted steel? It is. Maybe it doesn't look as nice. Some people, like if you buy a boat and you have an option of different trailers for your boat, it's usually cheaper to get the galvanized bunk trailer than it is to get the powder-coated painted roller trailer. Okay, I prefer bunks. It's a lot easier to load and unload in my opinion, but I wouldn't pay extra for the powder-coated painted one. It looks nice, sure. It's got a nice, can match the color of your boat, red, black, green, whatever, on your trailer. The galvanized one is going to start to look really kind of white and oxidized after a few years, but it's never going to rust. And the powder coating shouldn't either, but the powder coating will chip off from rocks and scratch off and things like that. So there's galvanized fasteners in this picture. There's a galvanized metal pail. Let's take a look at the galvanizing process. And this is a promotional video for the Galvanizers Association of America or something like that. So they're selling you on how great galvanized is. But I like the video because it shows a lot of different ways that it can be not only applied but used in the real world where you might see things that are galvanized.
An artful sculpture glinting under the sun. A sturdy bridge arcing over a rushing river. A beautiful architectural wonder. All these steel structures utilize hot-dip galvanizing for corrosion protection. Throughout the world, new technologies and creative chemistry continue to evolve this 150-year-old process. Once used only for corrosion protection, hot-dip galvanizing is now specified for its cost-effectiveness, versatility, durability, longevity, and sustainability. Hot-dip galvanizing, protecting steel for generations. Hot-dip galvanizing is the process of immersing fabricated steel into a bath of molten zinc. A wide variety of shapes and sizes can be galvanized, from small nuts and bolts to large structural beams to intricate artistic pieces. Galvanizing facilities are available throughout North America, and steel can be galvanized year-round. Prior to immersion in the zinc kettle, the steel must be chemically cleaned to remove all oil and grease, dirt, mill scale, and oxides. After cleaning and drying, the steel is immersed in the molten zinc. The 98% pure zinc bath is heated to 830 degrees Fahrenheit. While in the kettle, the zinc metallurgically reacts with the iron in the steel to form a series of intermetallic layers. After the steel is removed and cooled, it is inspected to check the zinc coating thickness and appearance. Any sharp grips or spikes are removed, and the thickness is measured. The final look of the galvanized coating can vary from piece to piece. The appearance is determined by steel chemistry, zinc bath composition, and cooling rates. Whether bright and shiny or a matte gray, the final visual appearance does not affect its corrosion protection. While hot-dip galvanizing is primarily specified for its superior corrosion protection, it may also be chosen for its durability, maintenance-free longevity, environmental sustainability, and aesthetics. Steel is an abundant and efficient building material, but when exposed to the atmosphere, it immediately begins to corrode. The hot-dip galvanized coating provides 3 levels of corrosion resistance: barrier protection, cathodic protection, and the zinc patina. The hot-dip galvanized coating effectively protects steel from the environment, providing barrier protection. Galvanizing also provides cathodic protection, meaning the zinc will corrode first to protect the underlying steel. Even if the coating is scratched, the surrounding zinc will continue to resist corrosion of the steel. As zinc is exposed to the environment, it naturally forms byproducts on the surface known as the zinc patina. The zinc patina further slows the corrosion rate of the zinc and acts as an additional environmental barrier. Galvanized steel products deliver proven durability, even in harsh conditions. The intermetallic layers formed in the galvanizing kettle make the coating harder than the base steel. This provides unparalleled abrasion resistance. Galvanizing also provides uniform protection. The zinc coating grows perpendicular to the steel, so corners and edges have the same thickness as flat surfaces. The immersion process also ensures hollow and tubular structures are evenly coated and protected inside and out. Because of its maintenance-free longevity, hot-dip galvanized steel is utilized in some of the harshest environments. Commonly used on structures exposed to the atmosphere, galvanized steel can provide over 70 years of maintenance-free corrosion protection. Hot-dip galvanizing is commonly used to protect steel embedded in soil and concrete or submerged in water. Galvanized steel has a proven record of longevity in all of these environments. Maintenance-free longevity also delivers economic value. The final cost of hot-dip galvanizing can be amortized over the entire life of the project. Hot-dip galvanized steel is highly sustainable and provides many environmental benefits. Zinc is a natural element, essential to life, and abundantly found in the Earth's crust. Zinc and steel are 100% recyclable, making galvanized steel safe for future generations. Galvanized steel offers an attractive, natural finish that blends with its surroundings. But if the natural metallic gray finish does not suit the project, the coating can be painted or powder coated for additional aesthetic appeal.
All right. So benefits over paint, that galvanized finish can take a scratch. And if paint takes a scratch, it's going to start to rust around that scratch, underneath that scratch, and rust underneath the coating of the paint. Galvanized will always protect around that scratch. So it might rust where it was scratched, but it's not going to spread. Use caution. Some of you might remember that first week of lab, as I was going through the stations, I said we never, ever, ever bring the propane torch from the copper pipe over to the galvanized sheet metal for doing our soldering of galvanized sheet metal. Does anybody remember why I said that? Yeah, well, I didn't say you could die. You could, I guess. We can heat up galvanized sheet metal with an iron, but we never want to heat it up too hot, or we start to burn that zinc coating off of there. And when we burn that zinc coating gives off fumes, and those fumes can make you really sick. Okay, so we're always going to use caution when we're dealing with galvanized sheet metal. Metal fume vapor, the zinc shakes, the Galvi flu, those are some of the names that have been given to that when people get sick from breathing in those fumes. And it happens over the course of time, typically, not just in one shot, but it's not something we need floating around the lab. Caused by exposure to fumes from the zinc oxide or the magnesium oxide coating smoking off of there. Okay? In extreme cases, loss of consciousness within a matter of minutes, chronic cough, bronchitis, things can develop over time. So we want to be careful with galvanized coatings. All right, so putting this sheet material into a shape. We can buy it in different stock, maybe corrugated tin. Where might we see something like this on the left? Roofs, maybe the sides of pole buildings and farm buildings, right? Coiled up pieces might be something I might take and then run through a machine that has something done to it, a process or a series of steps to create maybe siding or rain gutters or soffit and fascia material for your house. Okay, those are just a few things we might see around town on our houses. Thickness of any of that metal is commonly referred to as gauge. So our 11 gauge sheet metal for welding and cutting, all the way to our 23 gauge sheet metal that we use for our toolboxes. Notice that as the number gets larger, the thickness is actually less. We weld on 11 gauge, our toolbox is 23 gauge. So as the number gets higher, the thickness goes down. Let's take that stock and let's make something. Whether it's sheet by sheet, or maybe more commonly off a large coil, we can take that stock and start to go through some different processes here used to create something, a usable part or product out of that stock. So there's a pretty long list right here, and this isn't even close to everything that we could do to sheet metal. Bend it, curl it, stamp it, roll it, form it, laser cut, water jet, all kinds of things we could do to that sheet stock, anything less than a 1/4 inch thick to make a usable product. Let's take a look at some of these. Curling. Not rolling a stone across the ice, but curling, forming the edges into a hollow ring, eliminates a sharp edge. So where might you have seen metal that has been curled over underneath itself, making a round edge? That's a hem. On a toolbox we have a straight edge, not a round edge. Good thinking though. If I were to round over the edge, how about in like camping cups and bowls and plates and things that might be metal for camping? Okay, a lot of times they're powder coated, blue with white speckles or whatever. But your bowls and your coffee cups and things like that that are metal would be rolled over. Why would we curl over the edge of a coffee cup? Yeah, you're going to look like the Joker otherwise, right? We're going to take that sharp edge off of there. Expanding, you see this in the lab over on the portable oxy-fuel stations. Here in other applications, maybe a set of stairs on a mobile staircase to reduce the weight. Pretty common for park equipment, playgrounds, picnic tables, things that can shed water. Okay? And a lot of times those outdoor applications then are also coated with a plastisol. How many of you have been in plastics class? Okay? So you use plastisol in plastics class, right? Liquid at room temperature, heat it to a solid protective coating on this expanded steel. Sometimes people call this mesh. It's expanded steel. It's got cuts put into it and then it's pulled. So we can also make a piece go a lot further, right? Cutting or stamping slits into it and then stretching it out. So we have water flow through, air flow through, reduced weight. Laser cutting. We have a laser cutter next door. The laser cutting of steel usually requires an assisted gas. We don't have ours set up that way, so we usually just laser cut and engrave wood. But laser cutting using a high-powered focused laser beam in a computer, in a computer program to cut out pieces. Maybe we're cutting out little pieces that we're going to use somewhere else. Maybe it's just used for decorative cutouts. But either way, we get a really nice high-quality cut, very accurate cut. So laser cutting is one of them. Press brake forming. Press brake. Kind of sounds a lot like this piece of equipment over here, right? The pan brake. Pan brake is used to bend angles. The press brake, we could put different forms in there and different shapes. And you can see the picture on the left. Maybe we're making a housing for a piece of electronic equipment or something. So it works a lot like the pan brake. Typically, this would be hydraulic, meaning what? Hydraulic power? Right, ours is mechanical power, right? So all we do is bend as strong as we are and just use a little bit of mechanical assist. Next would be pneumatic, using what? Air, okay, compressed air. And then hydraulic, okay, using a fluid. Hydraulics fluid is not able to be compressed. Air is. So we lose a little bit of power transfer when we use pneumatics. If I push on one end with 100 psi, I might only get 80 psi on the other side because the air compresses. Fluid doesn't do that. If I push on one side with 100 psi, I got 100 psi on the other side. Fluid does not compress. So it's a little stronger. We can bend maybe thicker metals with it. Roll forming. This is very common. Some of you may have even seen this happen before. A continuous bending operation. If you look at the picture, this would be done in steps. We can't just go from flat to our final shape. We have to go through some steps, because if we just go right to our final shape, we're stressing the metal too much. So we're bending it a little bit more, a little bit more, a little bit more, and then the final roller puts it into its final shape. Now, you might have seamless siding on your house. You might have steel seamless siding. I've got vinyl siding. I put it up in 12-foot lengths. But steel seamless siding, a company, one of the companies around here is called ABC Seamless. And they would come to your house usually with just a van. And on that van, they've got their roll forming equipment and a coil of whatever color you wanted. So you had them come out, a week or two ahead of time. They measure your house. They figure out how much material you need. They'll give you some different options for finish. Well, do you want it to look like cedar? Do you want it to look like pine or whatever? You'll pick an embossed finish on it, so it's got a texture. And you can pick a siding profile. Do you want Dutch lap? Do you want shiplap? How wide do you want it? And what color do you want it in? So when they order that, the coil is already colored for you. It'll roll through the first machine to give it the embossing that you wanted, so it looks like wood. And then it'll roll through the next set of rollers to put it into whatever profile you wanted. Shiplap or Dutch lap siding. And then the best part is it'll cut it to length. So they'll measure for a piece and they'll be like, this one needs to be 22 feet and 6 3/4 inches long. They cut it to that exact length. They can put it on your house, and there's no seams on that whole 22-foot long section. You can't buy something like that at Menards or Home Depot. Okay, they're about 12 feet long. So seamless siding could be done this way. Gutters, the same way. I have had seamless gutters put on before, and they can measure, say this piece needs to be 24 feet long, and they run the coil through the machine, and it comes out in the shape of a gutter on the other end. Spinning. I got a video that goes along with this. This is pretty cool. You can take a piece of metal, and it's a flat piece of metal, right? And spin it at high speed, and as it's spinning, we can push on it and form it against a shape or against a die, right? It takes a while to make a product, okay, a little bit, and by a while, you'll see in the video, it takes them probably about a minute. So you might be thinking, wow, that's pretty quick. I could make something in a minute. Yeah, you can, but typically in sheet metal, we're like boom, 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 boom. We want to make like 20 parts a minute, not one. But in this case, maybe we're making a nose cone for a rocket or some cookware. What you might see here in the video, I think they're making like a cake pan or something like that. Let's take a look at this. Stamping. Stamping, any number of operations that can be done using sheet metal. Okay, this can include making a profile, trimming things, okay, cutting them to their final size, maybe piercing or punching holes where things are going to get fastened through later, or deep draw forming, making deeper parts, almost like vacuum forming, those of you that have been in plastics class. So a stamping process could do any of these things or all of these things in one process. It all depends on how you set up the machine. Okay, being able to make a profile cut to size with holes in it, all ready for the next process.
Multiple operations may be carried out on sheet metal stock either at a single die station or at multiple stations within a single stroke of the press. Dies used in single station operations can be either compound dies or combination dies. Compound dies are press tools in which only cutting operations are done, usually blanking and hole punching. Combination dies are press tools in which a cutting operation, usually blanking, is combined with shaping or forming operations. Multiple station operations are done with dies that have several stations. Each station simultaneously performs a single step in a series of operations needed to complete a part. Finished workpieces are discharged with each stroke. Multiple station operations can be performed using either progressive dies or transfer dies. In progressive die operations, parts are made from continuous coil stock and remain connected to the stock by a carrier strip during each successive operation until the final cutoff and discharge from the die. In transfer die operations, parts are blanked before or at the beginning of the sequential operations. Mechanical transfer devices grip and move the individual workpieces from die station to die station within a single die to complete a progression of operations. With large workpieces, a tandem press line may be utilized. Parts are transferred by gripping devices from press to press, instead of within a single die. Each press within the tandem line holds its own tooling and performs specific operations to form, trim, and pierce the part.
Water jet. There's no notes for your water jet, but a really cool video here on the water jet cutter.
A steel fender built for a custom motorcycle, and a ballistic-grade material designed for bulletproof, blast-proof armor. They're among the strongest engineering materials around. But today, they'll both be cut down to size by one of the world's most powerful forces. Forget about bubble baths and designer bottled water. This is the Seattle Research Lab of Flow International, the world's leader in ultra-high pressure, or UHP, water jet cutting. So why is water a cut above a welding torch or diamond-edged saw blade? It all begins simply enough. A hydraulic pump takes in regular tap water and pressurizes it. For water, increased pressure through a small aperture equals increased velocity. And since, as we all remember from school, force equals mass times acceleration, increased velocity means serious sliceability.
You can take a very small fraction of Niagara Falls and concentrate it in a very small beam, and that will be able to cut very hard material. Just like laser, we focus the light to make a laser beam.
The water is forced through this tiny opening, which is ringed with a gemstone so it won't be cut to shreds by the water jet. Just like constricting a garden hose with your thumb concentrates a stream of water out of the nozzle, concentrating a volume of water through a tiny opening produces this. At the business end of the jet, the water is traveling faster than any jet plane at Mach 4, 4 times the speed of sound, at a pressure of 87,000 pounds per square inch.
So at that point, it's really one of the most powerful water jets on Earth.
Super Soaker's working on that technology right now. 87,000 PSI, you'll be able to slice your enemies in half. Fastening sheet metal. So now once we have these parts, we will put them together. You guys are very familiar with rivets. Rivets come in all different diameters and all different lengths. Threaded fasteners, we talked about using like galvanized screws and stuff like that on a deck, or even ungalvanized stuff like you're probably pretty familiar with machine screws, but we have to drill a hole first. Other screws we don't have to drill a hole first. Yeah, some are called self-tapping, where they have a little cutter on the end. Others are called self-piercing, where they're actually tapered to a point, very sharp point, and they'll just pierce right through and then thread their own hole as they go between pieces of metal. Another one here is resistance welding, sometimes called spot welding. We used to have a spot welding machine here in the lab. It doesn't work very well with galvanized sheet metal. The tips of the spot welder would get corroded all the time from the zinc oxide coating. But essentially what spot welding does is, you can see in that picture on the lower left, as we drop down on the metal handle, the two tongs pinch together. And if there's two pieces of metal between those two tongs, overlapping pieces of metal, it sends an electric current between the two tongs, and anything that's pinched between them. So as that electric current flows very well through a conductor like copper, it doesn't flow quite as well through something like steel. So what we have there when it doesn't flow well is we have resistance, which creates what? Heat, right? We talked about that from day one. So that resistance creates heat, and now we have a little melted, molten nugget, and those two pieces are actually welded together. Resistance welding or spot welding. So resistance welding or spot welding is a method used to join overlapping pieces of sheet metal. The two electrodes clamp the metals together, and then a quick jolt of current flows through the electrodes and through the pieces of metal that are pinched together. Creates a little nugget. That resistance causes heat, and the two pieces are welded together in a little spot. Hence the name spot welding. Okay? Works through resistance. The resistance of the metal between there is a little higher than the resistance of the excellent conductor of copper. You'll see robots doing this a lot. If you've ever been in any factories where they're, especially cars, if you ever get a chance to tour a factory that makes cars, there'll be robots running these spot welders all over the place, knowing exactly where to be, pinched together, a quick tack, quick tack, quick tack. Your door panels are put together that way. If you look at your car, you'll see a bunch of little round holes when you're looking at the paint, or little round spots where the nugget of molten material is. So here you're seeing it done in an auto plant, fastening things that were probably formed on a stamping machine, right? Earlier in the press, so the sheet metal was formed, profiled, had holes pierced in it, openings for windows and door handles and mechanisms, and then placed over one another, overlapping, and then the robot can come in, or an operator carrying the spot welder can come in and spot weld those individual pieces. Can also be done on a roller. So this is done on a line. Look at that. Same process. Electric current runs from one wheel to the other and through overlapping pieces of metal. All right. Is that it for your notes? Okay. We've got a couple of videos here. One of them is making toolboxes, and the other one is making car door panels. Okay, let's take a look at these two videos.
Thinking inside the box can be a good thing if you want to organize your tools. And of course, we're referring to the toolbox. Proper tool storage keeps any work site running smoothly and efficiently. And today, you can really go big on the concept with units designed for mechanics and other pros. With a professional toolbox, you'll never have to rummage around for the tool you need. There's a place for practically everything in one of these mega tool chests. It starts with a coil of heavy-duty steel. It unwinds into a punch press that cuts the metal into panels and punches holes for later assembly. Each of these panels will be transformed into a toolbox drawer. They feed the panels into an automated bending machine. It folds them on 3 sides to create the back and sides of the drawer. It also folds over the rim. This adds strength to the drawer and gives it a smooth edge. The assembler slides the front panel onto the drawer, then an automated welding gun reinforces the seams and secures part of the lock mechanism. To build the toolbox cabinet, a worker arranges stiffeners and lock bar grids on the back wall. Then it's over to a lineup of computerized welding guns. These guns fuse the stiffeners and grids to the panel. Each part gets numerous welds to ensure the unit really holds up. The cabinet's sidewalls are next. Workers prop them up with supports as they weld the panels to the back wall. With the toolbox right side up, they install the top. They turn the cabinet around and, working from the open front, slide the lock bars into their slots. Then they build the front framework and weld ledges for the drawers to the support grid. They add a panel to the bottom end of the cabinet and weld the entire perimeter. Now it's into the paint booth, where spray guns coat everything in a layer of powder paint. The paint is tough and solvent resistant, so it will hold up to oil spills in a garage environment. They install the rest of the locking mechanisms on the front of the cabinet. Then, using a guide, press the adhesive-backed logo into place. They now snap the drawer slides into holes on the cabinet's side walls. These slides are equipped with roller bearings, which will enable the drawers to open and close smoothly. Here, they make use of the holes punched into the drawers earlier. A quick click, and the drawers are fastened to the slides. The drawers come in a range of sizes to accommodate tools of different proportions. The shallow compartments will hold wrenches and screwdrivers, while the larger ones have been made for the big power tools. Workers now encase this mega tool chest in plastic and cardboard. But this job is not quite wrapped up. They tip the unit on its side and send it down the line to get wheels. The pre-packaging prevents dents and scratches along the way. A worker bolts casters on each corner of the cabinet to allow it to be easily moved around in a garage or any other work site. Add-ons can be purchased for these tool chests, so the storage possibilities are virtually endless. And that's an organizational approach that you can't really mess with. Car doors have come a long way over the last century. They're lighter for improved fuel efficiency and stronger to better withstand the force of an impact. They also now contain a lot of electronic gadgetry like speakers and power windows, all of which enhances the daily commute. A car door is one of the first things many people reach for as they start their day. So let's unlock the mystery of how it's made. It all starts with carbon steel, an alloy that's strong yet malleable. Machinery uncoils and straightens it. A large blade slices it to the desired length, producing sheets called blanks. Then it's over to a powerful press. This particular one is a trial press, which offers a better view of the process than the one on the production line. The press forces the blank into a die, giving it the basic shape of two car doors. It's a design that's been engineered for both aerodynamics and strength. Back on the production line, the main press is churning out car doors. An automated device with fingers then grips the newly shaped steel and transfers it to a punch cutter. It separates the two doors and trims the excess metal from the edges. With the outer door panels now complete, a handler inspects them for bumps, dents, or scratches. He approves only those that are absolutely flawless. The next worker arranges the window frame, a reinforcing plate for the hinge and the inner door panel, all in a special clamping fixture. Its fingers grip the parts to hold them in position as the fixture rotates and two robots move in to weld them together. At the next station, the worker arranges steel bars and tubes on a robotic platform. They add strength to the door, so it will better withstand any impact. He places the inner door panel over the bars and tubes. The robotic platform angles the parts for welding. Another robot applies adhesive to the rim of the outer door panel. More robots dab adhesive at strategic locations. Those dabs match up to the tubes and bars on the inner panel as they made it to the outer one. A special press then folds the lip of the outer panel over the inner one. This hemming gives the assembled car door a neater edge. With the inner and outer panels now joined, the car door undergoes rust-proofing, paint, and other protective treatments. Now, over on the assembly line, a worker fits the handle into its niche and bolts it to the door from the other side. Chrome trim is clipped into place. Moving down the line, a worker installs a small fixed window in the groove of the frame. He uses a plastic protector to prevent scratches as he slides the larger window into its slot in the door and links it to a powerlifting mechanism inside. He separates the two windows with a metal divider. At the next station, this car door gets an automated side view mirror. They're now ready for the inner panel and its workings. The employee wires the panel to the door and snaps it into place. He tests the power windows and they close to a tight seal, indicating a successful installation. A special elevator now lowers the completed car doors 6 meters to the next station. A worker unloads each door with the help of a pneumatic arm. This device shoulders the weight of the part and correctly positions the door for installation. He drives bolts into hinges to attach the door to the car. On the door side, the heavy-duty reinforcement plate surrounds the hinges and supports them. The whole weight of the door will hang on this plate as it swings open and shut. With all the panels installed, it's time for the final adjustments. They call this finessing. They examine each panel to confirm that it's flush to the rest of the car body, and they tweak the installation job where needed. Finally, they're satisfied the assembly is airtight, so it's time to close the door on this production.